Okay, well, thank you so much for inviting me here. So let's see. Today I'm going to talk about sort of new way to study shallow structure, and this work is in collaboration with Miyake Ishii at Harvard, Victor Tsai at Brown, and Adrian and Francisco in UNAM in Mexico, and also student Yangshan Lee at U Chicago. So the overall outline of this talk is going to be just talking about first why we care about the shallow structure. And then I'll talk about some of the conventional methods. And I'll introduce this new approach and apply this to real data sets. And then I'll summarize. So in earth sciences, we have most of these observation at the surface. So here we have elevation, and also the colors are geology. And if you are making geochemical observation, they're also at the surface. And one of the major role of seismology here is to connect these observation with what's going on in the deeper part of the earth. And one of the issue is sort of conventional way of imaging the earth using, for example, travel time, looking at how fast the wave travels. If you look at the global tomographic models or large scale models, they usually don't have as good of a resolution in between the surface and a certain depth. Here, this model basically starts from 100 kilometers or so. But as you know, this depth is really important for understanding plate tectonics. That's basically where plate is sitting on. And going into a bit shallower depth, we have in crustal earthquakes, which is the majority of the earthquakes that are damaging, and the faults are there, and we would like to understand the earthquake physics, and there we would like to understand shallow structure. Even going shallower, about top 10 to 100 meter depth, we are calling them critical zone, where air, organism, and soil, water, and rock, so this bio and fluid earth really interact with the solid earth. That's the critical zone, and we would like to understand what's the architecture of this shallow structure here. Now, another important reason to study the shallow structure is for earthquake ground shaking. So here you're seeing a simple cartoon of earthquake coming in. So for the same earthquake, depending on which site you're sitting on, here you have more of a high velocity hard bedrock site. Here you have low velocity or sedimentary basin sort of a site. And you can see the records here. And not only the amplitude is big here if you're sitting on this site, but there's also this reverberation coming in after. So it's really important to characterize what sort of shallow structure is right under you. And really good example of this is from this Mexico earthquake that happened in '85. So that was magnitude 8.0. So epicenter is here. So it happened near a city called Campos. So this is recording, and this is an acceleration, and this value is the maximum acceleration you got. So as you get farther from the earthquake, as you expect, the shaking is decreasing, but only not until you get to the Mexico City. Then you actually have much higher amplitude here, with the maximum value actually exceeding what we had at the city of Campos. And that's because the Mexico City is the basically prominent sedimentary basin. So unfortunately, because of that, we had a lot of damage in Mexico City, which is the most populated area, more than 5,000 casualties and so on. And even though the earthquake actually happened quite far from Mexico City, we often call it 1985 Mexico City earthquake. So that's another important reason to study shallow structure. And a parameter that earthquake engineers like to use is called VS30, which is basically shear wave velocity of top 30 meters or so. So we're talking about really shallow structure there. So this plot is showing you sort of the effect of VS30 on ground shaking on the y-axis. If you compare this case where VS30 is about 1 kilometer per second, note that the unit is in meter per second, to a case where it's 100 meter per second, then you see sometimes more than even 5 times of amplification there. So in order to study this shallow structure like VS30, most direct way to understand that is to drill a hole and get a sample. And you can measure the sample in the lab and measure velocities, density, or anything that you like to measure. You can also put a source here and receivers at different depths, for example, and measure how fast the wave travels back and forth. So that also can give you some idea about the shallow structure. But now this is, of course, the most expensive way to do this, and it's invasive. So what's often done is actually local seismic survey, where you have this vibrator truck in this case as a source that emits the seismic wave, and these red dots are basically sensors or geophones that are receiving these signals that travel through the subsurface and come back. So we analyze this information to study this subsurface structure. Now, this vibrator truck is also pretty expensive. So if you don't have such resources, then you can be the source yourself. So this is actually myself here, hitting the still plate that's in gray here. And these red dots again are actually the geophone sensors. So this I've done in at Harvard when I was doing my PhD. So this was just like a course project. I actually had to hit multiple times since I wasn't strong enough to get the good signal to noise ratio. We got the sort of the image at the subsurface. We got sort of a low velocity structure right underneath here or so. And we found that that was correlated with actually some heat pipe going through that area. So you just saw basically my first and last field work of my whole PhD. And actually, this is basically what USGS do as well. They go to all these sites in US, especially the places where it's prone to earthquake hazards. They would go and measure, do this survey and measure VS30. About 90% of them are done using this local survey type. Only 10% of them would be this borehole drilling type measurements. So you can see that there are a lot of also gaps in this measurement, and it would be also good to fill in those gaps. So to do that and study the near surface structure today, I would like to introduce a new method, and I would like to do that by looking at what's called polarization. And by polarization, I mean the direction of particle motion. So to make it easier to understand, let's assume earthquake is sitting right below the station. There's actually a real data example of something close to this. So this is an earthquake that happened in Japan at depth about 280 kilometers or so. And the horizontal distance to the station is about 20 kilometers. So it's really more or less the vertical incidence of the wave. And in order to measure the directions, we need 3 component seismometers. So here is the vertical component. That's north and east component here. And we know that P wave has particle motion that's parallel to the ray path here. So in this case, we would expect the P wave to be recorded more or less at the vertical direction. And actually, just by using that information, you can almost just pick out the P wave here. For S wave, we know the particle motion is perpendicular to the ray path. And by using that fact, we expect S wave to be more or less in the horizontal component, and we can actually pick out the S wave there. And in general, earthquake would actually come in at a certain angle, and I would be actually measuring this particle motion, and that's basically becoming my data. So if I were to actually summarize this whole talk in 1 minute or so, what's happening here is conventionally, seismologists, we would like to measure how the travel time of the P wave and S wave from the earthquake time and use that for imaging the structure. But here, rather, we're looking at the directions of this particle motion, and that becomes really sensitive to shallow structure. So that's the point here. So here, I'll try to give you some intuition for this. So we are trying to use the angle I here that's measured from the vertical to actually constrain the velocity v at the near surface. So if we think about Snell's law, that tells us that sine angle over v is constant. And in seismology, that constant is called we call it ray parameter, and it's some value that's given for if we knew the earthquake and station locations. So now if we had lower velocity at the near surface, in general, we would expect smaller angle to keep that value constant. If you had higher velocity, then you would expect larger angle like that. So that's sort of the intuition of maybe we can use these angle information to actually study the near surface structure. So that's the intuition, but here now I'm going to tell you that the problem is actually not as simple as that. So here what I'm going to do is actually do a sort of the derivation of a case where P wave is coming in. And let's assume we know the material properties with P and S velocity here. And let's try to measure this angle and see what's the relationship of this angle to this velocities that we want to study. So some of you might find this derivation boring, but the reason why I'm going through this is actually, to me, this is one of the most exciting part, the result of this. So please bear with me. So the reason why this is actually not as simple as what I just showed you is because as soon as P wave hits the free surface, it also generates the reflection of P and S wave. So what we are observing at the surface actually is not just the incoming P wave, but also reflected P and S wave all together at the same time. So we need to do some vector summation here. To do that, we need to know the direction and amplitude of these vectors. So let's say the direction of P wave coming in is, let's say the angle is I. And because of the Snell's law, the reflected P wave should have the same angle I because the VP is constant. Now you're changing P to S velocity. So we have to have smaller angle for S, which I call IB here, because Vs is smaller than Vp. So we have something like that for the angle. For the amplitude, let's see. Yeah, before we go into amplitude, since this is constant, as I said earlier, just note that this angle I is only function of Vp. This angle IB is only function of Vs because this value is constant. For the amplitude, let's assume just P wave coming in has unit amplitude of 1. Since we're going to just derive the angle, it really doesn't matter. For the reflected P and S wave, this is what we call in seismology reflection coefficient at the free surface. basically what it tells you is we're just solving for the free surface boundary condition. So for non-seismologists, you can try to understand this as, for example, P wave is coming in, it hits the surface. Now that it needs to decide how much energy it would like to make it go to the P wave versus S wave. So it actually ended up being a function of both Vp and Vs in this case and that case. So you can sort of expect that now that the angle I bar that's measured at the surface is probably not the same as the angle that's coming in. And now we can derive that by this relationship where tangent of the angle would be all the sum of all the horizontal components of this vectors and all the vertical component of these vectors. So you can basically do amplitude sine times cosine, amplitude times cosine, amplitude times cosine, and sum them all up. So that would be horizontal, and you can do cosine and get the vertical. The point is that because of this relationship with this amplitude as being function of Vp and Vs, each of these terms are a function of both Vp and Vs. But if you actually go through this derivation, what comes out of this is quite interesting because it comes out as this bizarrely simple result. It just comes out as tangent to IB, which means this angle I bar here somehow is just exactly twice the S reflected angle. And this should be actually surprising for you because this angle IB, as I mentioned earlier, is only a function of Vs. So even though we're looking at sort of P wave data, this is actually only somehow dependent on Vs and not at all to Vp. So that's quite puzzling, and it's not really intuitive. I still don't have intuitive explanation for this. That's what theory tells us. So if any of you have good explanation for this, I would be happy to hear. So even though this result is actually not well known, I would say still in seismology, but actually we weren't the first to derive this. This was actually derived for more than 100 years ago by this person called Vichert, 1907. So he exactly had this derivation at that time. So the reason why he was interested in doing this derivation was because he was one of those first people who actually made this seismograph. So he really wanted to understand what he is recording. So in his case, he had this derivation, but here we're actually going to use this result to actually study the shallow structure or VS here. So just to summarize this part, P wave is not sensitive to Vp, so that's not very intuitive. And another interesting thing to think about here is that in seismology, we would like to study VS structure using maybe S body wave or surface wave data. Here we are saying that this is P body wave, which is usually much higher quality and higher frequency, and it has information about VS. So from VS point of view, it's sort of one of the highest frequency information you can get in seismology. Now we can do exactly the same thing for S wave. I'm not going to do all the derivation in this case, but it works all the same. Only difference is that we're just measuring the angle for the direction that's perpendicular to the particle motion, because that's how S particle motion works. But other than that, it's all the same. And the result actually in this case comes out intuitively in a sense that the observed angle is actually dependent upon both Vp and VS in this case. So this means that we can combine both P and S data and constrain both VP and VS. As I mentioned earlier, P data is only sensitive to VS. S data are sensitive to both VP and VS. So you can tell already that VS would be much better constrained because it's got more data to constrain it. And not only that, actually P data are much higher quality than S data. So let's just try and apply this to real data. So let's look at a site, a seismic station that's sitting in Japan. That's called AGMH station. And we're going to use all these green dots. Those are the earthquakes. There are about 250 events. And they are sort of far away and intermediate and deep. So they are about magnitude 6 and above. So we are using most of those earthquakes in that criteria from 2004, which is basically when this station started operating. And we have just some signal to noise cutoff at 2. So let's just pick one earthquake here and look at the data, and that would look something like this. So here we have 3 component data, vertical, north, and east component. And you can see that most of the energy is in vertical in this case. So actually we are looking at the P wave data here. And what we can do is take, for example, this time window and translate that to this 3D space. And basically as time goes, the particle motion is doing something like that. So now we have to measure the angle. So to do that, we are basically doing principal component analysis. It's basically just metrics computation where you're looking for the most prominent eigenvalue or eigenvector in this case. So we get the most prominent eigenvector, and that gives us the direction that's basically the most representative of this particle motion. And basically I can just measure the angle from vertical, and that becomes my data point here. So if I do that for all the earthquakes and both P and S wave, I get about 220 P angle, 130 S angle. S data are less just because of the lower quality data there. So now what we are going to do is to combine all these data and try to find the best matching, best fitting VP and VS value here. So we can just do that with simple grid search. So here on the horizontal axis, we have VP going from 0 to 7 kilometers per second. And here on the vertical axis, we have VS going from 0 to 5. And the colored region is where the search region, this is basically not physically possible region. The bluer, the less misfit to the data, so the better. So I was pretty happy about this because it's only 2 parameters in this case. So takes really maybe a few seconds on my laptop. And another thing is that you can see the minimum is quite well defined. So that's another good thing here. So since it's fast process computation anyways, what we can do here is also do some bootstrapping analysis to get some idea about the uncertainty of VP and VS. But you can already tell from this grid search result where the ellipse is in a way such that you will have much larger uncertainty for VP than VS here. So that's confirmed by this bootstrapping analysis. We randomly resample the data and do the analysis again. And basically, these are the distribution of values for VP and VS. Again, you see much more contracted distribution for VS. So we can basically take the mean value as our final estimate and the standard deviation as our uncertainty. So those are our final estimates for this single site station. So now we are going to expand this to all the stations in Japan. Japan is great in the sense that their station coverage is really dense. It's about, actually, it's closer to 800 stations now. So it's really densely covering whole Japan. So if I got VS or VP value at each site, I can basically get a map of near surface structure in Japan. The other good thing about this data or these sites is that they actually already measured these VP and VS values at each site. So I can use that to use as a benchmark to verify if this method is working well or not. So for the earthquakes, I'm going to use exactly the same sets of earthquake that I showed for the single station analysis that I just showed you. And the single station is actually part of this HiNet network. So it's sitting here. So what I'm going to show in the next slide is basically the VS value, the final estimate we got as a color here. I'm going to talk about VS only in this talk, but I'm happy to discuss VP results as well. So that's the VS map of Japan. Red is slow velocities and blue are faster velocities. And as I mentioned, they have benchmark for this, where they actually drill the hole at each site. And I can do one-to-one comparison, and it looks something like this. They're in the same color scale and everything. So yeah, I was quite happy about this. And there are lots of interesting features that we can look at here too. For example, this is sort of simplified geotectonic map of Japan. And the blue color is where the oldest part of Japan, and lighter color is younger part of the Japan. And one feature that's often talked about in Japan is MTL, or median tectonic line, that's here. And actually, we might be picking out such zone here. If you see, there's quite a big contrast between red and blue, and the red part basically corresponds really well with the MTL line here. The other thing is that the blue part, the older part, more consolidated and perhaps more faster, we would expect. And we see some of that in here, for example, here the blue, older part correspond to blue, maybe here as well. But what we don't see is actually this part is quite a contrast, where it's blue on the right and red on the left. So we actually found out that we have much better correlation with the topography. And that part I just pointed out was one of those prominent basins in Japan. So there are several there. And we see consistently low velocities in those regions. And we usually expect higher velocity for a mountainous region, because if you think about it, in order to sustain certain slope, we have to have rigid materials, and faster velocities are expected. But in that gray shaded area, you see actually pretty low velocity, even though it's quite mountainous and slope is pretty high. And one thing we found that's interesting is that we have also correlation with these volcano locations in Japan. This is something we didn't think about when we were doing this study. We thought we would be contributing to seismic hazard problems mostly, but this shows that maybe we can also contribute to volcano hazard problem as well if you're sensitive to such features. Now, some of you might be wondering about what depth we're looking at in these values. So in order to answer the question, I would like to introduce another dimension to this problem, which is frequency. So we can think about this simple scenario of having low velocity layer at the top that's increasing gradually. So this is 3-layer case. So let's imagine doing this analysis, but for high frequency wave, that would be sampling the shallowest layer on top there. Then we would expect the velocity of the top layer to be recovered from this method. Now you can lower the frequency or make the wavelength longer, where it samples both of the layers. Then we would get some kind of average between the first and second layer and get the value corresponding to that. That would be higher than the red value. You can go even lower frequency, then we would get probably higher velocity here. So that's just a thought experiment here. So I was really curious, well, how much is this velocity frequency dependent really? So I tested that with, again, another station in Japan, but this time, what we call broadband station that can record quite broad range of frequencies, so I can play around with different frequency band. So when I did that, this is the result. So I did exactly the same analysis. So it's all VS here, just with different central data frequency. And you can see that it varies from about 1.7 kilometer per second here to about 3.2-ish kilometer per second there. So it's actually varying quite a lot, showing that it's really frequency dependent quite strongly. And that 3.2 value is almost reaching the value what we think of in seismology as an average upper crust value. So it also gives some sense that, okay, as we go lower frequency there, we're really reaching quite deeper depth there. So another really great data set to do these things, the broadband data, is actually US array that's covering whole US. So this is really good chance for us now to really fill in those gaps we talked about earlier. So this is actually preliminary result, but so this is the result for 1 second wave there, and I can go down to lower frequencies in 2-second and 3-second period. You can see they're a bit more scattered in 1 second map. We think that's because the shallower, as you get shallower, we have much more contrast and varying velocities at shallower depth, and it's becoming more consistent with surrounding values as you go into 2 and 3 seconds. Now we can also bring back this geological map we looked at earlier. And there are actually a lot of things going on, but I'm going to just point out several features here. So one thing that comes out in all the maps quite clearly is this feature that delineates more of a sedimentary region here, and that comes out as low velocity structure there. And what's also interesting is, for example, in that region, you see quite fast velocity here, but that's not what you see in 1 second. So it changes very quickly as you go from 1 to 2 seconds. And similar thing happens in Florida too, where it's more homogeneous in 1 second map with the surroundings, but it becomes much faster than surrounding as you go into 2 and 3 seconds. And these are consistent with our knowledge where, for example, in Florida, we have quite shallow basin depth, and that's followed by bedrock at already quite shallow depths. So I think that's what we're seeing here. Another interesting feature, so maybe we can look at here. So that's where the velocity changes really abruptly from fast on the east to slow on the west. Somehow it happens to be sitting on between Minnesota and Dakota border. And that is also something we see at the surface too in geological map. Again, we have more sedimentary region on the west side here. Now, what's interesting is we can sort of try to track this boundary as we go in 2 and 3 seconds. So as you can see, the boundary is moving actually to the west a bit as you go into 2 and 3 seconds. So now what we can do is actually have the surface observation and actually try to extrapolate into depth and can tell, oh, this actually boundary is actually dipping to the west. So we really now start to be able to do that kind of thing. We can also bring back this image of the Earth and try to see if there's any common component between these. We are actually not sampling so much depth here. So there's actually still a lot of gap, I would like to note, between this 3-second map and 100-kilometer depth. But if we assume it's more or less continuous, then it's possible that this boundary we see here is continuation of these features still, in which case we can say, okay, this boundary is dipping to the west a bit, and then it's more or less consistent to the depth. We also see this low velocity features that's prominent in 2 and 3 seconds. That also might be continued there in the map if you see there. So this is to say that we can now try to connect the surface to the depth image at the depth that we already have. Now we're working on, okay, how can we try to convert these velocities, which I showed as a function of frequency or period, as a function of depth. And to work in that direction, this is sort of a average depth sensitivity we got for this kind of analysis, which is in vertical axis here with the unit of meter, and horizontal axis which is in frequency in hertz. As you can imagine, this is not only function of frequency, but also the absolute velocity themselves, because we need to go to depth or length dimension from frequency or period, we need to actually have the absolute velocity with the frequency as well. So at 1 hertz, we are basically sensitive to about 100 meters to about less than a kilometer here, depending on what your absolute velocities are that are in color. And we just saw in US map, if you go to 2 and 3 seconds, you're getting deeper like that. And if you go to say 10 second or 0.1 hertz, then that's where you get into this upper crustal, the crustal area of 1 to 10 kilometers or so. If we go into the other end here, going to about 10 hertz, then we are sensitive to 10 to 100 meters that could be able to sample this critical zone here. So hopefully I have convinced you now that, oh, it's hidden there, but that's basically my title. The important part is still there. So we can actually study the shallow structure by measuring the angle and not really the timing. So first we showed that this method, actually, yeah, all it needs is just a single station as long as it's 3 component, and it's non-invasive and it's really fast in computation. And one thing that's still puzzling and interesting is the P wave data is not at all sensitive to VP, but only sensitive to VS. From study in Japan, we know that we confirmed that this method actually works and does correlate with surficial features that we observe. And from analysis with different frequencies, we can actually think about now velocity structure that's varying over depth and extrapolate over it. I didn't have time to mention this, but since you're measuring all these angles over the time period of stations operation, so we can actually detect a lot of sometimes issue with the stations as well, because then angle will be problematic. For example, you can imagine vertical component not working, then you can see the angle wouldn't be right. So that can be actually used for things like ocean bottom sensors, where the stations are really hard to get to. There are a lot of things to do on this direction using this method. One thing that could be interesting, I would point out among this is also we can study depth-dependent anisotropy, because we can, in this study, we basically just assumed everything was isotropic, but if there was anisotropic structure, then you can see variation in angle in different directions and so on. And you can also extend our depth-dependent velocity analysis as with the depth-dependent anisotropy structure. So eventually, hopefully, we can really try to fill in this gap with maybe what we can call polarization tomography. So that's what I have here. And for the last 1 minute, I will just show something that I'm excited about quite recently, which is using 3D printing for seismology. And this is basically, the color here is the velocity model, or you can think about it as geological structure. And we are printing this with 3D printer. And this is not for just visualization. This is actually printed in a way such that these different regions here are actually representing the realistic heterogeneity of the structure. So we can use that to actually do seismic experiments using source and receiver and actually get the record. So this would be sort of completely new way to simulate this seismic wave, but in the lab. So this can be used to tackle difficult problems that are hard to do with conventional numerical studies. For example, you can think about what's the effect of topography on earthquake ground shaking, which is really small scale and difficult problems. So you can think about tackling those kind of issues, or basin interfaces that are complex in 3D volume. How can we deal with that? That's another problem we can try to tackle. So if you registered to last year's AGU, you can still watch the talk on this. And another topic I was recently working on was related to deep earthquakes, and I'm sure some of you are interested in this, and I'm happy to talk about that as well. And I'll leave you with this conclusion slide again. Thank you very much.